Hi, I'm Will Melville, and I'm excited to talk about baseball fielder positioning. And I'm actually going to start with a TikTok from John Boy Media that I really love. So this is the Rockies playing the Marlins. And the thing I love about this video is we get to watch the Rockies coaches strategizing in real time. So he's waving fielders around. They're discussing things with each other. So right here he says, you want to close the gap. So they're using their coaching experience, their intuition. They're trying to figure out how to position against a really good hitter, Luis Arraez. And of course, Arraez just hits it into an empty outfield. And Arraez has a great quote at the end. So yeah, that video is moving kind of fast. So if you missed it, Arraez said, I'll paraphrase, he said, I saw that there were 6 infielders, so I wanted to hit it in the outfield, and then I hit it in the outfield. Which he makes hitting sound really easily. I don't think it's that easy, but he's obviously very good. And if you missed the Rockies positioning, this is a screenshot of it. And if you can't tell by now, I really love defensive positioning in baseball. I think it's fascinating. I love that video because I love watching the Rockies reason about how they wanted to position. They were obviously leaning on their coaching experience and their intuition, which I don't have any of. I don't have any coaching experience. So if I want to be able to reason about positioning strategy, I need to rely on math. So that's what we did for this project. We came up with a math problem that would give us positioning strategies. And specifically, we're identifying the positioning strategy that's going to minimize the expected value of some objective function. And to be a little more specific, we're taking the expected value over a batted ball trajectory distribution. So that's D in that formula. And what are we taking the expected value of? Our objective function. So that's a function of the batted ball, B, which is drawn from that batted ball trajectory distribution. And it's also a function of the positioning strategy, PS. And we actually came up with 2 different objective functions. The first one was WOBA, which stands for weighted on base average. And for those of you who may not know about WOBA, it's related to runs by an affine transformation. So minimizing WOBA is equivalent to minimizing runs. And then the other objective function we came up with was negative outs. If you minimize negative outs, that's equivalent to maximizing outs, which obviously you can imagine a defense might want to maximize outs. So now I'm going to do a little bit more of a deep dive on some of these pieces, starting with the batted ball trajectory distribution, so D in that formula. So if I give you a batted ball spray angle, launch angle, and launch speed, there are physics models out there such that you can then calculate the full trajectory of that batted ball. And that's obviously useful for positioning because if I know where a ball is landing and how long it's taking to get there, I know where I need to stick my fielders to try to catch that ball. So we wanted to be able to use that full trajectory when we were optimizing. So for every batter, we estimated the joint probability distribution of spray angle, and launch speed. And then that allowed us to sample batted ball trajectories for all the hitters, and then we could optimize over those batted ball trajectories. Using, of course, our objective function. And so our objective function, again, that's a function of the batted ball B and the positioning strategy. And there were 2 of them, WOBA and negative outs. And we estimated these using logistic regression. And we intentionally chose to use logistic regression because it's a linear formula. So it's easy to calculate the gradient. Specifically, we can calculate the gradient of our objective function with respect to our positioning strategy. So then when it comes time to figure out an optimal positioning strategy, we can approximate it with gradient descent using those gradients that we can calculate. And this is what that looks like when we run it on Shohei Ohtani. So you can see how the positioning strategy evolves as gradient descent runs for Shohei Ohtani. And then if we run it on all 2023 hitters, this is what it looks like. Again, gradient descent is evolving our positioning strategies for every hitter. Now we can take these 2023 recommended positions and we can look at 2023 batted balls and we can see how well our positioning works compared to an MLB average positioning strategy. And when we do that, we get these results. So first, if we look at the expected batting average allowed, With our positioning recommendations, we allow an expected batting average of 305, and compared to MLB average, they allow an expected batting average of 320. For WOBA, our positioning allows 308, and MLB average positioning is 321. Now remember I said WOBA is related to runs by an affine transformation. That's that third column there. So if I apply that transformation, I get the third column, which is weighted runs above average. For our positioning, it was negative 520, and for MLB average, it was 156. And then if you just divide that by 30, you can get per team. Ours was negative 17.3, and MLB average was 5.2. So we look at this table and we say our positioning saves 22.5 more runs per team than MLB average, which is pretty amazing. I was thrilled. But I actually want to take a poll of the audience. Raise your hand if you don't believe me, if you don't buy it. Okay, some brave souls don't buy it. My co-authors don't buy it because they know what's about to happen. I don't buy it either. I don't believe it. And the reason I don't believe it is because of that first video we watched with Luis Arraez. He looked out and he saw 6 infielders, and he said, well, I'm just going to hit it in the outfield. So how do I know that as I'm moving fielders around into my recommended positions, how do I know the hitters aren't seeing that and going, well, I'm just going to hit it somewhere else? So there's this underlying assumption that I can move fielders around and they're going to hit the ball in the same place. And I don't know if I believe that assumption. So we decided to test that assumption. And what we did, we took all of the data. So this is pre-2023 shift band. We took all the data where batters were shifted against and all the data when they were not shifted against. And for each batter, we fit separate spray angle distributions to those 2 data sets. And for most batters, we found that they're pretty similar, meaning they're not changing their spray angle significantly when a shift is on versus when it's not on. But we found a handful of hitters, like Chas McCormick, who we show here on this slide, who appear to go more oppo when a shift is on versus when it's not on. So that naturally raises the question, what do we do against a hitter like Chas McCormick if when we shift against him, he's just going to hit the ball the other way? And in general, what do we do against an adaptable hitter? So we're going to define an adaptable hitter as a hitter that's choosing their batted ball distribution from a finite set of multiple batted ball distributions. Then we're going to rely on zero-sum game theory to solve for an equilibrium positioning strategy. And that's the positioning strategy that's going to minimize the expected value of our objective function under the assumption that the batter is choosing their batted ball distribution to maximize the expected value of the objective function. So if you think in terms of runs, we're choosing the positioning strategy to minimize runs under the assumption that the batter is observing that positioning strategy and then choosing their batted ball distribution to maximize runs. So if we think about Chas McCormick, we can assume that he's choosing between the orange, more pull-heavy distribution, or he's choosing between the blue, more oppo distribution. And then we can solve for an equilibrium positioning strategy for Chas McCormick. And when we do that, we get this result. And I'm actually not going to spend much time on this result because I think the next example is much more interesting. And that example is Joey Gallo. So Joey Gallo, to me, and probably to many of you, he's sort of the face of shift victimhood. He's a very pull-heavy, left-handed hitter. And back when shifts were allowed, he tended to be shifted frequently and very extremely. And in this photo on the left, you can see one of those very extreme shifts that the Astros used against Joey Gallo. And I look at that photo, and I see opportunity. I see a wide open left side of the field, and I think, gosh, if he could just hit it over there somehow, even if he just laid down a bunt, that would be perfect. So that's what we're going to consider in this example. We're going to assume that Joey Gallo can either choose to swing away normally and use his normal batted ball distribution, or he can lay down a shift-beating bunt, which is a bunt to the left quadrant of the infield, where the third baseman would normally stand if he's not in an extreme shift. And then just like we did with McCormick, we can solve for an equilibrium strategy. So this plot on the right shows our equilibrium strategy for Joey Gallo, but we're just showing the third baseman in this plot because the third baseman's the only fielder who really moves around in this example. So that blue triangle, that's the third baseman's position, recommended position if we assume that Joey Gallo is going to swing away normally. The orange triangle is the recommended position if we assume that Joey Gallo is going to lay down that bunt. And then the black X is the equilibrium positioning strategy. And then in the table on the left, we have the expected batting averages for different pairs of batted ball and positioning strategies. And there's two takeaways I want you all to have from this table. The first is, in the equilibrium, Joey Gallo is supposed to swing away, and that gives an expected batting average of 226, which is 3 points higher than if he swings away against the shifted defense. So by threatening to bunt when that's advantageous, by being adaptable, Joey Gallo forces the defense to move their third baseman in, and then he rewards himself with 3 more hits per 1,000 than he would otherwise get. So another way to think about that is, as a hitter, if you can be adaptable, you're likely going to benefit in the long run. And then the other conclusion I have from this table, which many of you may have noticed the huge number in this table, 574 batting average if Joey Gallo bunts against the shift, which is almost hard to believe. So I look at that number and I think, gosh, why isn't Joey Gallo just bunting all the time? And I began to wonder, well, maybe bunting's really hard. Maybe he can't do it. So I Googled Joey Gallo bunting to beat the shift. And this is the first video that pops up. And this is over 2 minutes of Joey Gallo bunting to beat the shift. And it's an awesome video. We're probably not going to watch all of it because I want to save time for questions. But I encourage you all to look it up after this. Google it. Google Joey Gallo bunting to beat the shift. Watch the whole thing. Enjoy it like I did. And then hopefully by the end, you'll agree with me that Joey Gallo is fully capable of bunting to beat the shift. And he really has no excuse to not achieve that 574 batting average against the shift. But to wrap things up, if you're among the many people who didn't raise their hand earlier and you believe that hitters don't adapt based on what fielders are doing, then we came up with a method to position fielders that's going to reduce expected runs allowed compared to MLB average. If you are one of the brave souls who raised their hand and you think that some hitters might adapt, we also came up with a solution to find an equilibrium positioning strategy against adaptable hitters like Chas McCormick. And then my final conclusion, which I'm actually nervous to say out loud, it's very controversial, but I think Joey Gallo should bunt way more often. And that's everything I have. Thank you.
Super interesting. That was fun. My first question is, oh yeah. So when you go to the adaptable batters, tell me if this is right. You are assuming they have a finite number of strategies that they can choose from.
Yep.
And that you know the distribution of each of those strategies. But
yep.
In reality, if you're where you can move your fielders is sort of a continuous distribution. So you could imagine that there's sort of a continuous array of choices that the batter is making. Is there a way to adapt this to be on a continuum rather than either or?
Not that I know of, but the way I think about it is the batter's decision is sort of on a continuum just because, like, even very skilled batters, I don't think they have perfect control over where the ball is going. And so that's why they're choosing a distribution and not a point. And so because they're choosing a distribution, it is on a continuum. Like Luis Ariz, his distribution is probably very wide. He's capable of hitting it all over the field. And we don't know necessarily where he's going to hit it, and he doesn't necessarily know. Maybe he's trying to hit it to the outfield, but there's a large amount of uncertainty in that, and so that's why we're sampling from a distribution. So it ends up being on a continuum in that sense, but yeah, you don't have a continuous decision space. And even in like the extreme case, like you could have a hitter who's like, let's assume a hitter's like can choose his spray angle with perfection. Like you could still discretize that to like 90 spray angles, and that would be not technically continuous, but fine enough resolution that it's close enough probably to continuous.
Yeah. Okay. I believe that. That's yeah. Although you need a lot of data to get reasonable estimates of all of those 90 distributions.
Yes.
But yeah. So my other one is that so it looks like you looked back in time for when the rules changed about the shift.
Yeah.
So having looked at all that data, what is your recommendation to MLB about what the rules around the shift should be?
Well, I don't care about the fans. I only care about my own self-interest.
Yeah, that's fair.
As you guys can hopefully tell, hopefully I've got this point across, I love positioning. I think it's so cool. So my vote would be no constraints at all, and just let teams go crazy. I love the crazy alignments.
Let the boys play.
Yeah.
How many runs per inning, per game, per season difference do you think this would make? Let's say between your original non-equilibrium, non-game theoretical arrangement of defenders versus the game theoretical equilibrium optimum.
Yeah, so I kind of glossed over, like, we tested how many hitters are actually adapting to the shift, and it was actually like kind of hard to find hitters who adapt. So I think not doing the game theory is, for most hitters, that's gonna like hopefully work out fine. But I think there's probably a handful of hitters where you would be worried about them adapting. But yeah, like if you just across the board assumed every hitter is static, I think you'd be fine for the most part. The bunting thing, like, it's kind of funny. We did all this math to figure out you should move the third baseman in, but if you just like pay attention next time you're watching a live game, most teams already do that anyways. Like against lefties, for the first 2 strikes, they'll have the third baseman in case they're thinking of bunting, and then they get 2 strikes and they move back. So, yeah, I think the game theory is, at least in the bunting case, it's like we're modeling something that's already been observed by infield coaches, and yeah.
I really don't have a question. It's more or less a comment. I think that you did a really good job. Whenever I'm looking at presentations, a lot of times I look at the very beginning, and with the TikTok, I think that was very original. It was very different, so definitely like eye-catching for sure. Actually, I do have a question. So with the weight on base average, can you just talk about that part again? Just to make sure that we have like a really good understanding when it comes to that.
Yeah, so I first learned about it from Keith Law's book called Smart Baseball, and he explains it really well. And I will not explain it well, unfortunately, because I'm not a writer, but he describes it as like if you asked someone who didn't know what batting average was or slugging percentage, like if you knew nothing about baseball and you said, I want you to come up with a statistic to evaluate hitters, they would probably come up with something like WOBA. So the way it works is each outcome of a plate appearance has an expected run value. So like a home run, for example, it's going to score at least 1 run, but then if there's runners on base, it'll score more runs. So the expected run value of a home run, I think, is like 1.5 or something. So then weighted on base average, it's taking those expected run values of all of the events, and then it's just multiplying it by the number of times those events happen, and then dividing by plate appearances, basically. Someone out there is probably like mad at me for explaining it slightly wrong. It's like slightly different than that, but that's the basic idea. It weights baseball outcomes in terms of runs.
We already said you're controversial, so it doesn't matter.
Yeah,
so
okay.
we're good. That's all I have.
Okay.
All right. Thank you.